Okay, so we have seen the shift registers in the first part of this chapter. Now we will carry on with the counters. In the chapter 5, we have seen how we can implement a counter. So if you do remember, we have done a state diagram 0, 0, 0, 1, 1, 0, 1, 1. So this was one of those examples. So when it is 1, we were jumping from one state to the other, and it goes back. Otherwise, if it is 0, we hold. So you can check chapter 5 that we have done a similar example like this. Now, this is a typical wraparound counter, which we have used 2 bits. This can be extended to 3 bits as well, or 4 bits counter. So with the 3 bits, we count from 0, 0, 0 up to 1, 1, 1. Okay, so that's going to be 0 to 7. And then if it's a wraparound, it goes back and starts again like this one. Okay, so this is a wraparound counter. Now, the clock is working, train of pulses. Again, we have got a asynchronous reset. And when it is 0, it's activated. When it is 1, it's not activated. That's why it's active low. Now, Q0, Q1, and Q2. So we have got 3 bits. Let's say this is Q2, this is Q1, and that's Q0. And 0, 0 at the beginning because of the reset. On the next clock, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 3, 4, 5, 6, 7, and then returns back to 0 and starts again. Now, we are actually using counters to track the time or count the particular events, which you are going to see them later in another course, how we are using counters. As this is a wraparound, it goes back and starts again, and it counts up again. Now, these counters can be implemented with different types of flip-flops, and they can be either synchronous or asynchronous. So if we look at slide 16 now, you can see that a binary ripple counter, which is this operation over here, is demonstrated with 2 different types of operations, with T-type flip-flops and D-type flip-flops. Now, what we can see over here, as you can see, the clock is feeding in the first least significant bit flip-flop, and the rest are not feeding with the clock. So it's actually asynchronous. So what is happening here? The clock is activating the first flip-flop, and the first flip-flop output is actually triggering the second flip-flop clock. Then second flip-flop output is triggering the third one, and third flip-flop output will trigger the fourth flip-flop clock. And they are all, as you can see, falling edge, okay, because of the bubble. This can be demonstrated with D-type flip-flop as well, with a similar approach. Again, the clock is fed in, okay. Now, D is fed back from the Q prime, and the output of Q is fed in to the clock, output of Q is fed back into the clock, and so on. Now, as it says, each count is initiated by the falling edge of the clock, starting from the top. As you can see, you can have it as a rising edge by eliminating that bubble. Enable input can be also added in order to have parallel load. And this is also going to be using a max input to retain or to count. We can do that. And ripple counter can be implemented also with JKs. So what you need to do for JK, in order to implement JK, you just need to have short JK inputs together to implement the T-type, if you do remember. So we can have a JK flip-flop, Q bar. Okay, so J and K inputs are tied so that you can have T inputs. Okay, this is also possible, and then you can have the similar implementation like this. by using that approach. Now, this is a ripple counter which we are using for binary numbers. We can also have a ripple counter for BCDs, like BCD ripple counter. We can demonstrate as starting from 0, 0, 0, BCD numbers 0 to 9. So 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then if it's going to be wraparound, it will go back and start again. So this is counting from 0 to 9, binary coded decimals. Now, we can use again D-type, T-type, or maybe a JK flip-flops in order to implement it. And this is also demonstrated with the circuit over here. Now, again, the clock is fed into the first flip-flop, and the rest are just triggered based on the output cues. Now, how can we operate this? We have got Q1, Q2, Q4, and Q8. Now, Q1 is, as you can see, is changing after each clock pulse. Okay, so the clock is changing, Q1 is going to change. Now, this is going to, as Q1 is triggering Q2, Q2 is going to complement every time. So how is that going to happen? As Q1 goes from 1 to 0, and as long as, because the Q8 prime is coming in from here, as you can see, to the J, and K is coming down as an enable for all of those, okay? Now, what we are going to look at, as Q1 goes from 1 to 0, and Q8 is 0, this is actually going to be 1, right? So that's going to be 1. Now, as this is 1, and this is 1, as enabled, both 1 is going to complement Q2. So Q2 is going to complement until the while the Q8 is 0. Now, when Q8 becomes 1, okay, now this is going to be 0. So if this is 0, okay, then what's going to happen? Q2 is going to remain at 0 because it's going to reset it. Okay? So J is going to be 0, K is going to be 1, and that's going to be reset. So Q4 complements every time when Q2 goes from 1 to 0. So as Q2 is triggering Q4, now Q4 is going to complement when J, which is enabled, and K is enabled. So whenever Q2 is activating Q4, as both are 1, it's going to complement Q4. Okay? Now, Q8 remains at 0 as long as Q2 or Q4 is 0. And when Q2 and Q4 becomes 1, then Q8 complements. Okay? So Q2 and Q4, as they are ended here, now that's going to be when they both becomes 1, then this is going to be 1. So J input is going to be 1, and K input is also 1. Then Q8 is going to complement. And when Q1 goes from 1 to 0. So we can implement binary code decimal counter based on this approach. And this is also a regular ripple counter, but it cuts off from 9 as it is a BCD. And we can easily implement 3-decade decimal counter. So this is going to count up to 9. Then this one will trigger this one, another 10 to the power 1 digit. This will count up to 9, and then this one, okay? So 999 can be obtained from BCD counters calling as 3-decade decimal counter. Now, these are examples of these two, actually, or three implementations using T or D or JK. They're showing the asynchronous implementations for the counters. Now, you might say, why are we using this? This is just showing that how the output is triggering the next input, the next clock input of the other flip-flop in order to perform the operation. Now, we can say that with the asynchronous, the state changes on the flip-flop and does not happen at the same clock edge, so it's not synchronized. Now, the flip-flop associated with the least significant bit is synchronous with the clock input, as we have seen it over here. And the rest of the flip-flops change after a number of flip-flop propagations. So this is going to propagate Q2, Q2 is going to propagate Q4 and Q8 and so on. So there's a propagation delay over there. And we can say that the maximum propagation delay for asynchronous counters increases linearly with the number of counter bits or the number of flip-flop stages. So for which in this one we have got 4 flip-flops, so we have got a 4 delay. Let's say if we have got 8 flip-flops, that's going to be 8. Now, there's a trade-off over here. Now, if the counting speed is more important than the counter size, then we have to use synchronous counters. But if counter size is important, then we can use asynchronous because clocking needs extra routing space and area. Okay, now we can easily modify the binary counters like we have done in chapter 5 and connect all these clocks to each other, so synchronized, and based on that we can arrange the combinational circuits required for the flip-flop in order to make a binary up counter. So this is, as you can see, all the clocks are connected together. Now they are synchronized. They're not coming from outputs. And these are outputs are fitted in with the count enable so that it can trigger one each other and counts up to 000 to 1111, for example. Okay, this is not BCD, this is just an up counter. So as this is a 4-bit, it starts from 00, it can go up to 111. And the clock is all on the rising edge. Once again, if you have any questions, please note those down and you can ask me in the live lecture. Now, we can also have, this is an up counter, but we can also implement an up-down counter. Now, up-down counters, again, we have to decide what will be the operations. So, for example, we have got 2 inputs up and down. Okay. Now, when up is 1 and down is 0, it counts up. Okay. When up is 0, down is 1, it counts down. And when both are 0, it's hold. And let's say 1, 1, 1, it's going to count up again. So count up has got the priority. Okay, so we can easily, again, implement this using multiplexers. So with 2 inputs that we can use, up and down, and multiplexer, we can easily implement that using T-type or JK flip-flops. So again, T-type flip-flops, the multiplexer and OR gates, up and downs are there, and we can easily use those to implement up-down binary counter. So either using T-type or D-type or JK flip-flops, these can be easily expressed. Now, you might say, why are we going too fast and how do we derive those? In chapter 5, we have seen how we can derive those inputs, which ones are connected to where and so on. So that's why in this chapter, I'm just showing how we can connect multiple of those to implement a 4-bit, for example, or 8-bit up-down binary counters. Okay, the idea is same. First, we have to derive the state diagram, then the state table. From the state table, we have to find out flip-flop input equations in order to derive these combinational circuits, put them onto a K-map, find the optimized expressions, then draw the circuitry. So this is the circuitry that we are going to obtain in the end. And that's for up-down counter. Now, what we can do as a modification, because D-type flip-flop, actually, in order to implement a T-type flip-flop, we can use D-type, as we have said in chapter 5. So Q bar. Now this is going out as Q. Now D-type is like T XOR Q, right? So we can use this as a D input. Now T is coming in, and it's also feeding back from the Q. And the clock is coming in. Okay, if you want, you can also add reset. So that's also a reset can be in the game. Now, this is a typical implementation of T-type flip-flop by using D-type flip-flop. Now, we can also modify the counter so that we can have different operations. What type of operations are we looking for? For example, we can add the clear, the clock, the load input, and the count, and we can use different operations. Like when clear is 0, we don't care about the clock. If it is an active low, then we don't care about the load, we don't care about the count. It's going to clear the count, okay? So clear the registers for the counter. Then when clear is 1, so we are deactivating it. When it's on the clock rising edge, if the load is 1, we don't care about the count. We just load the inputs into the counter. Again, clear is inactive. The rising edge, load is 0, so we load it. Next, what will happen? We are going to count up. We start to count. Okay? So after load, the count is 1, and we start to count. Again, on the rising edge, 0, and the count is 0, then no change. We hold wherever. So, for example, we load in clear everything, the outputs are 0, then the clear is 1, then the clock rising edge, load is 1, I load, let's say 0, 0, 1, 1. Then on the next rising edge, if the count is 1, I start to count 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, and it goes like that. When the count changes to 0, I stop there. I wait until the count becomes 1 again, and I will carry on. Now, implementing this, once again, it's possible using different type of flip-flops. Again, over here, we are having a multiplexers, which is similar to what we have done. And we can easily implement it, deriving the input equations and finding out what will happen based on these control inputs. It could be not difficult to derive it. So implementing BCD counter using a parallel load counter. Now we can have two approaches. So how does this going to work? If you look at it, there's a counter, the inputs are coming in, and those are going to be your outputs. So BCD counter with a parallel load. What do we mean by that? Now, BCD, if I go back to BCD, where we have got it, 0 to 9 that we need to count. Okay? So 0 to 9 we need to count. Now, what is this AND gate is doing over here? I will explain that. Now, as we are counting, we start from 0 inputs, okay? So we start from here. Now, we are counting up. Now, what we need to detect, when it reaches to 9, it has to activate the load. So the load will be activated, and we are loading in 0, 0, 0 again, okay? And the count will be 1. Okay, so how are we going to do that? Now, what is changing over here? When it reaches to, let's say, A3 and A1 is equals 1. So when both of those are 1, I can say, okay, A3 and A0, not A1. A0 is 1, which represents 9 for me. Then I can say, okay, please reset my counter or load and leave data. So that's how we can have the load input going in from the AND gate. Okay, so when the load input is activated, what will happen? Inputs are going to be loaded in as 0, 0, 0, 0. Okay, so this will load in 0, 0, 0, and then count will start again, and it will count up until 1, 0, 0, 1, then load again. You can also use a clear, which is a active low. This is also possible, and you can load it. Be careful with the clear inputs and the load inputs over here. They are both possible. Okay, so load is active high and synchronous. Clear is active low and it's asynchronous. So two possible ways of implementing it. Now, counter design that we have seen in chapter 5, it's actually demonstrating us how we can use combinational circuits together with the flip-flops in order to implement them. And as counters are easy to implement, we know how to count if it's not a random count, we can easily design them without going into too much details. So, for example, if we want to demonstrate a count with a JK flip-flop, let's say we have got this example. The president state is given, next state is given. So 0, 0, 0, 0, then 0, 0, 0, 1. So it goes over there. 0, 0, 1 to 0, 1, 0. Down here. Then 0, 1, 0 to 1, 0, 0. You can skip sequences. That's not a problem. If there are unused, it's like a random counter. So 1, 0, 0, then 1, 0, 0 to 1, 0, 1. It goes there. 1, 0, 1 to 1, 1, 0. Okay, and 1, 1, 0, go back to 0, 0, 0. So these are the states that we need to implement using JK. Now, there are a few things that we need to look at, which I believe we are going to see details in that chapter in the live lecture, but I want to demonstrate it over here. Now, as we have got these, there is one thing that we need to learn about JKs and other flip-flops, which is known as excitation table. So what is this excitation table? Now, excitation table, it's actually depends on the characteristic table of the JK. Do you remember the characteristic table of JK? Now, J inputs, K inputs, and Q plus can be easily derived for the characteristic table. The characteristic equation was Q plus equals J Q prime or K prime Q, right? So 0, 0, 0, 1, 1, 1, oops, 1, 0, and 1, 1. Now, Q plus, based on this equation, when both inputs are 0, it's hold. When it is 0, 1, it's reset. When it is 1, 0, it's set. And when it is 1, 1, it's complement. Okay, this was the characteristic table. Now, the excitation table, we have got the present state, we have got the next state. Okay, so then we have JKs. So it's other way around, 0, 0, 0, 1, 1, 0, 1, 1. Now, we have to find out what's happening with JK inputs. So when the present state is 0 and next state is 0, it's actually two choices. Either it's holding the previous state or it's resetting the next state. So in both cases, J is 0, K is changing. So 0, K is changing, so it's don't care. Then 0, 1. Now, present state is 0, next state is 1. So what will happen? Either we are setting the output to be 1 or we are complementing the present state. So it's 0, now it becomes 1. So in those cases, J is 1, K is changing. So it's 1x. Then 1, 0. Now, Q is 1, Q prime is 0. So either we are complementing or we are resetting. So complement and reset. K is 1, J is changing. So K is 1, oops, K is 1, J is changing. And the last one, when both are 1, either we are holding the present state or we are setting the output to be 1. So J is 0, K is changing. So 0 and, sorry, K is 0, J is changing. And that's our excitation table that we need to have it. Now, based on that excitation table, we can easily rewrite our state table and find out what will happen to the flip-flop inputs. Now, as we have got in total 1, 2, 3, 4, 5, 6 states, we have to use 3 flip-flops to cover those. Okay, so those 3 flip-flops is actually going to be JK flip-flops. So we need to have JA, KA, JB, KB, and JC, KC inputs that we need to find out. Okay, now if I use that excitation table, now this table can be formed. Now, how are we doing that? Input A, present state A, next state as A, 0. So 0, 0, 0, 0, 0x. So 0x. Present state for B is 0. Next state is 0. 0, 0 is 0x. Present state for C is 0 and it is 1. So 0, 1, it's going to be 1x. So JC is 1, KC is x. And this is going to be repeated for all those 0, 0, 0, 1, 1, 1, 1, 1, and then 1, 0. And all these excitation table based flip-flop inputs are going to be derived. Now, as we have got these expressions or the values, then we have to put those into a K-map and find out the optimized equations. If we don't use the intermediates, so for example, we haven't used 3 and we haven't used 1, 1, 1. So 0, 1, 1 and 1, 1, 1 is not used. Unused states can be treated as don't cares. So based on JA, KA, and their values, and using Carnot maps, these equations can be easily obtained. And once we have got these input equations, we can just plot the logic circuitry as required. Now, the question here is if these states that we have got, and we have got the unused state 0, 1, 1 and 1, 1, 1. What if the machine started from unused state? So for example, if it started from 0, 1, 1 or maybe 1, 1, 1. Now, if it is started from here, then it will go to the next closest value. So 0, 1, 1 will actually jump automatically to 1, 0, 0, and 1, 1, 1, 1, 1 will jump actually to 0, 0, 0. Okay, so next upper closest position they jump to. And this is how we can use a counter design. Now, another counter that we can see in the literature is ring counter. Now, ring counter, as the clock is ticking, now what will happen? It's actually going around and starting again. So that's known as a ring counter. Now, how does it work? So 2-bit counter, okay? So 0, 0, 0, 1, 1, 0, 1, 1. And that 2-bit counter is activating 2 to 4 decoder. So if we demonstrate that, 0, 0, 0, 1, 1, 0, 1, 1. So we count from one to the other, okay, when the count is enabled. Now this is actually going to activate 2 to 4 decoder. So 4 outputs, D0, D1, D2. If you do remember decoders, one of those is going to be activated at a time. Right? Or if you want, you can put these as in the figure, it says T's. So just use T's. T0, T1, T2, and T3. Now, when it is 0, 0, T0 will be activated. When it is 0, 1, T1 will be activated. When it is 1, 0, T2 will be activated. And when it is 1, 1, T3 will be activated. So that's how we can have the timing waveform. Okay? So you can use a 4-bit shift register, and you can also have again, the ring counter implementation, and the register just needs to start from 1, 0, 0. That is also possible. Now, the last example for a counter is a Johnson counter. Now, the Johnson counter is a tail ring counter as known. Now, what will happen? So I can show you the implementation from the flip-flop outputs. Now, the first one is feeding in, okay? So 0, 0, 0, 0, okay? Then 1 is going in again. So 0, 0, 0, and then 1. So 1 is going to be like a shifting. So it's shifted, then 1, 0, 0, 0, it's 0 again. So it's 1 again, 0, 0, 1, 1, 0, 0. Then this is 0, that is going to be 1, 1, 1, and then 0, it's 0 again, this will be 1, 1, 1, 1, 1, and then this will be 0 this time. So 0 is going to fit in, so a switch tail ring counter can be obtained. Okay, so if this is 0, the 1 will be fit in. If this is 1, 0 will be fed in. And that's how we can implement a Johnson counter. So that's all I want to say about this chapter. This chapter is a simple and straightforward. It's a short chapter which is related with chapter 5, implementing 4 bits or 8 bits or different types of shifts, shifters, registers, or the counters by using flip-flops, synchronous or asynchronous operations. And I think this could be useful for your Lab 4 and 5. If you have any questions, please do not hesitate to contact me. Thank you.